When I look up at the night sky from Cambridge, I can only see a few dozen stars. From the dark mountaintops where I use telescopes, I can see thousands. Yet even this is a small fraction of all that's out there. Our Milky Way galaxy contains hundreds of billions of stars. And 70% of all of these stars are a type of star we call red dwarfs. But even from those dark mountaintops, you won't see a single red dwarf. Even the closest and brightest is too faint to be seen without the aid of a telescope. After 5 years of researching and learning and teaching about the stars in our galaxy, I sometimes imagine that I can see some of our galaxy's small red stars. What excites me the most about these stars are the planets we are finding around them. We are on a quest to find a planet like Earth, a planet similar in size and with the right temperature for liquid water, a planet with the potential for life as we know it. But finding a planet like Earth is difficult, and learning about what it's made of or what's in its atmosphere is even harder. With the methods we use to make these measurements, it is easier to find and to study planets around smaller stars. And the smallest stars in the universe are our red dwarfs. These stars are about a quarter the size of the sun, but hundreds of times fainter. Instead of emitting most of their light at optical colors like the sun, they emit most of their light in the infrared, where our detector technology has not been as advanced. Moreover, our theoretical models don't yet explain their fundamental stellar properties, such as size, age, or spin. As a result, these are one of the least well-studied type of star, and we don't yet have a good understanding of their physics. I'm intrigued by the mysteries these stars hold, but these uncertainties pose a fundamental problem for learning about the planets around them. The reason is that we measure the properties of the planet only relative to the properties of the star. So if, for example, we have any uncertainties about the star's size, we're similarly uncertain about the planet's size. Without knowledge of the basic physical properties of red dwarf stars, how can we hope to understand the planets that orbit them? It's to address this issue that I turned my attention to this type of star. Due to the uncertainties in our theoretical models, I take an observational approach to studying these stars. I used Harvard's Magellan telescope in Chile and NASA's infrared telescope facility in Hawaii, employing a technique called spectroscopy. For each star, the final result is a spectrum like this one, which shows the brightness of the star at different colors or wavelengths of light. I measured spectra for 600 of the most nearby red dwarf stars, obtaining thousands of individual observations. Each of these spectra contains clues to the star's properties. Atoms and molecules within the stars absorb light at specific colors, creating distinct spectral signatures. In this red dwarf spectrum, the deep troughs are due to absorption by atoms of aluminum and magnesium. I measure the depths of these dips because the strength of these features depend on the star's properties. I looked for patterns in the spectra, correlating the depths of features like these against different stellar properties. After carefully considering the many possibilities, I found new relationships between the depths of specific features and the star's temperatures, diameters, and chemical compositions. I calibrated these relationships using the small sample of stars whose properties we can directly measure. And then I took my calibrations and applied them to the stars that I had surveyed. Even though these are some of the most nearby stars to us, for many of them, it was the first time we learned about their properties with accuracy. I also took my calibrations and applied them to stars already known to have planets around them. One example is Kepler 372, a red dwarf star with 3 planets. Using my technique, I showed that the star is actually 15% bigger than we had previously thought. And because we measure the properties of the planets, only relative to the properties of the star, this means that the planets are 15% bigger too. This change in size can be the difference between a rocky, Earth-like planet and one with significantly more gas, like Uranus or Neptune. We live in an era where it is possible to point to a star at night and say, this star has a planet around it. But it is around the red dwarf stars that can't be seen that we have the best prospects for finding and studying habitable rocky worlds. It's the planets orbiting these stars whose atmospheres we will be able to study with the next generation of telescopes, and on which we will first have the capability of finding signs of life. By learning more about our red dwarf neighbors, I hope to accelerate us towards a future where we can ask and answer new scientific questions about the Earth-like planets that orbit other stars. Thank you.